Morning, guys. Happy Friday. How y'all doing? Main plan for today is we're going to close out chapter 7, talk about how gravity can act as a centripetal force. The floor is open for questions, but last section, several questions that I got involved upcoming tests and exams. So just to make sure everyone gets the same information, I will go over this again for you guys. Today is Friday, October 27th, and today we're closing out chapter 7, which is really just the first of 2 rotation chapters. So next week is also rotation. It's just technically called chapter 8, has its own separate homework assignment. So next week, 30th through the 3rd, is chapter 8. Week after that, chapter 9 through 10 is going to be week after that, November 6th through 10, is going to be a short chapter 9, which will be about pressure and buoyancy. And that'll be the last new thing we cover before the second test. It'll be a short chapter, so I anticipate finishing up comfortably within this week with time to start reviewing things. And that second test will be November 13th through 17th. Like last test, it'll take place over the span of the week during lab time, so you just show up during lab instead of a lab to take the test on any day of the week that lab meets. Again, Thursday is a myth. There is no lab on Thursday, so the 16th is not an option. But my goal here is wrap up through chapter 9, have test 2 up to and including chapter 9 this week, and then I will power through and get everything graded by the 20th so that you have your test back and don't have to worry about it over Thanksgiving. Because that is this week, around the 23rd. When we get back from Thanksgiving, we'll have one more short section on waves, just some additional information at the end of the semester about mechanical waves and sound, and then full tilt into review season for the exam after that, because the exam season starts here. Now, starting at about this point, I usually get asked non-stop when the exam is in addition to when the test 2 is. So I'll point that out for you guys as well, just to make the information available. PC blocks off specific exam periods for specific courses, and I teach 3 sections of this course, C, E, and F. This is E, but all 3 of my sections are identical, so the exams are all identical, so I don't care which exam section you come to, kind of like how I don't care which day you come to take your normal tests. So, C exam is Thursday, December 7th at 5:30 p.m. F exam is Friday, December 8th, 8:30 p.m. And E exam is 5:30 p.m. the same day. You can come to any one of those of your choice. And I will leave them written there until the end of the semester. I didn't write C, E, or F because that doesn't matter. You come when you come to which time you want to come. Questions, concerns about anything at all?
You said you come anytime?
Yep. And only one of them. It's not like a 3-parter or anything. You show up to one and you take it once. I just figure I'm going to be here during all those times, and I'll afford my students the benefit of picking when they choose to take it. So, main things in the schedule are test 2 this week on chapters 6 through 9. So, momentum, rotation, and pressure. The exam will be these 2 days, and that'll be on everything.
And our
Yes, homework is officially due by the 5th of December, since that is the last day of class, and therefore the last day assignments are officially can be due by. Doesn't mean I can't extend it if you need it, just means that's the official last day. Feeling good, I hope? I only go over this stuff to help you guys. I'm not trying to scare anyone. All right. So today we're going to close out chapter 7 with a discussion of gravity, which I enjoy, so I might very easily be distracted on space tangents. Forgive me for that. Also, feel free to ask space-related questions as they pop into your head, because I like this stuff. And universal law of gravitation is really the only thing we have on the schedule for today. So once we're done with that, we can head on to our weekend, and then next week will be the applied rotation stuff. So, why are we talking about gravity in a rotation chapter? It's because, if you'll recall, in our discussions of centripetal force, we pointed out how the force of gravity between the moon and the Earth is what acts as the centripetal force that causes the moon to rotate around the planet. If that gravity wasn't there, the moon wouldn't orbit the Earth, it would fly away, and then our oceans would die. And then where would we send our astronauts? Or get our food? Or oxygen? So, that force of gravity is very important. The problem is, how do you calculate the force of gravity between the Earth and the moon? How have we historically found force of gravity in this class? I tell you force of gravity? I do that sometimes, but what's the formula we usually use in here? I'm just placing my good marker. On test 1, when I asked, how do you calculate weight or force of gravity, what was the answer?
Mass times gravity.
Yes, and by gravity, what number do you mean? Very good. This has worked up till now because most, if not all, of our examples have taken place on Earth's surface. This number, the negative 9.8 meters per second squared, only works on Earth's surface. It is very specifically calibrated to represent the levels of gravity here and nowhere else. That number stops being true if you leave the planet. It stops being true if you climb on top of Mount Everest, because you're a different radius from Earth's core. It stops being true if you burrow into the Earth, because you're closer to Earth's core and the gravity is actually stronger down there. This only works on Earth's surface, and even then it's still a little bit inconsistent, because as it turns out, Earth isn't a perfect sphere. It's kind of squashed. It's a little bit thicker on the equator, so the gravity is actually weaker on the equator, as it turns out. And then again, also mountains mess it up as well. So we can't use m times negative 9.8 to determine the force of gravity between the Earth and the moon, because the moon is not on Earth's surface. If it was, we'd have a whole lot of other problems. So we need something else. And that is why, over the years, scientists have devised the universal law of gravitation. We're not just going to treat gravity as the thing that holds you to the ground of Earth. We're now going to talk about gravity as a whole, how gravity works in general across the entire universe. Hence why it's called the universal law of gravitation. Gravity is a force that acts between all objects with mass. If something has mass, it is creating a gravitational field, and that gravitational field attracts the mass of other objects. All objects with matter do this, and that includes yourself, because you're made of matter and you have a mass. If it's made of matter, it is actively creating gravity. And therefore, all objects in the universe are technically exerting gravity on each other all the time. Earth pulls on you, and opposite that, you pull on Earth, because you have your own gravitational field that the Earth is within. But it's not just the Earth. The moon exerts gravity, so the moon's gravity acts on Earth because the moon has mass. And we know the moon has gravity because people have stood on the moon, and because the moon's gravity is what affects our tides. That's why we need the moon. Furthermore, the sun obviously has gravity. The sun has a lot of mass, and the sun's gravity keeps the solar system working. And again, every single object with mass is constantly exerting gravity. There's even a gravitational pull between you and Pluto right now. It's just too weak to do anything about. The reason that force is weak is because of this formula. So when I say universal law of gravitation, I'm not only referring to just the definition of gravity, I'm also referring to this formula. That is the name of this formula. Because we can use it to calculate the gravity between any two objects in the entire universe. So this defines how gravity works everywhere. And what this formula tells us is that any two objects will have a force of gravity between them equal to big G, which is its own constant that I will address in a minute, times the mass of the two objects in question multiplied together, divided by the distance between the two objects squared. It's called r because we call it radius, but the fact that it's radius doesn't mean that you cut the distance in half. The fact that it's radius means that the distance between the two objects is the radius of the giant gravity circle that the planet creates. So it says radius, and it is a radius, but what it means for the sake of this formula is the distance between the centers of the two objects. And you can use this to find gravity between literally any two things, as long as they have mass, and as long as they are some distance apart. Literally any two things. This formula tells us that gravity is directly tied to the mass of both objects. This is why you can feel the gravity Earth exerts on you, because the Earth is gigantic, right? Earth's mass is enormous. So Earth is not always creating a lot of gravity, and so the force between you and Earth is very strong. However, your mass, compared to a planet, is cosmically speaking very tiny. And that's why you do not notice your own gravitational pull affecting other things. It's both masses multiplied together. Your own mass is kind of irrelevant without another object to cause the actual pull of gravity. So the mass of both objects is important, but so too is the distance between them. If objects are further apart, you're now dividing by a bigger number, and what effect does that have on gravity? If you divide by a larger number, what happens to the answer? If you divide by 4 instead of 2, the answer gets smaller. So the further apart things are, the weaker the gravity is. Inverse, if you pull two things closer to each other and this number gets smaller, the answer gets bigger. So gravity strength is not only the masses, it's also how far apart the two things are. This is why gravity on Earth does get stronger the closer you are to Earth's core, since Earth's core is the center of its mass, the center of its gravitational pull. And the closer you get to it, the greater the gravity gets. And that's why you dig down deep enough, everything's molten and on fire. Because the forces are so great that it increases the pressure, that increases the heat, and everything just melts. It's also why gravity does get weaker as you leave the planet. And again, it's why objects that are very far away from you, like Pluto, don't really affect you very much. Assuming that our space program doesn't get faster than light very soon, the Earth is the largest thing you will ever be near, therefore it's the single largest gravitational pull you will be consciously aware of. the sun's pull is very strong, but since we're orbiting it, we don't really notice it. Any questions about the formula itself at this time? Okay. I just realized I didn't mention G yet. So, there's one more variable here, big uppercase G. Note that technically uppercase G is not the same as lowercase g. They are technically different letters and they mean different things. Lowercase g is always this. This is only true on Earth's surface. Big G is a new constant called the universal gravitational constant because it is only used in the universal law of gravitation. This is the only formula that uses uppercase G. It is always defined as 6.67 times 10 to the negative 11th, and it's really just a number that we need to make the formula work. Its sole purpose is making this formula function. Newton was not the first person to talk about gravity, but Newton's work on motion and gravity got very famous. So historically, in terms of like European science, Newton is the one who wrote this down and got famous for it. And so Newton derived this constant by just working with the formula until it started working right. And it started working right when this number was in it. That's all it does. And you don't have to memorize it. It's just on your formula sheet. This is its only use. It's very specifically written right beneath this formula on the sheet. You got force of gravity formula right there. Big G is written right under it. You don't even have to memorize the unit because you don't really need it. It's a weird unit, and the unit only exists to make the formula work. It does technically mean something. It has to do with how permittivity and permeability of free space interact to allow gravity to propagate through the universe, but that's not what this course is about, so you don't have to worry about it. You okay with the formula thus far? All right, then let's practice it. You can use this to find the gravity between literally any two things, and that includes these two things. Let's find the force of gravity between two mundane objects, two 10-gram markers that I have sat 10 centimeters apart. Our formula, once again, force of gravity equals big G times m1 times m2 over distance between the objects squared. Big G is always 6.67 times 10 to the negative 11th. Our two masses here are both 10 grams. How many kilograms is that? Grams should be 0.01 kilograms, and note that that number is input twice, once for each of the two masses. If the masses aren't the same, it's not the same number twice, but here it's just the same mass two different times. And lastly, r squared, distance between the two objects squared. How many meters is 10 centimeters? 0.1, and only the 0.1 is being squared. I only bring that up because calculators are kind of dumb. Since this formula uniquely involves usually very weird numbers and also a squared, I usually mention how I input this into my own calculator, just to try to keep everything working correctly. So this is how I would input it. I like using the E to stand for times 10 to the power of. It's the same E that your calculator gives you in your answers sometimes. There's a button for it. So how much gravity are we looking at right now between those two objects?
Is it 6.67 e to the negative 13?
Yep. And E stands for times 10 to the, so 6.67 times 10 to the negative 13th newtons. You will never feel a force this small, not because it isn't there, but because the human nervous system is not that finely calibrated. This is probably not enough force to make a hair on your arm twitch, let alone cause anything that you can, any visible motion that you can track. But technically, it's there. There is that force of gravity right now between these two things. But because of much bigger forces like friction, they're just never going to visibly move on planet Earth because of it. The friction from the table is more than enough to keep them from drifting near each other right now. However, if instead of on planet Earth, you transported these two objects very far away from the planet into the void of space, no air, no measurable gravity from any other objects nearby, eventually the objects would drift towards each other. Because if you're in space and there's no other major forces nearby, and they are the closest two objects to each other, their own gravity will naturally eventually draw them together. And this is one prevailing hypothesis on how planets and stars form. Just matter in space is naturally drawn towards each other, and eventually enough of it gets close enough and clusters together until it forms either one big rock or one big ball of fire. But terrestrially, too weak to ever do anything with. And frankly, you don't have to recalculate anything. I'm just going to demonstrate something real fast. Let's say instead of the gravity between two markers, I wanted to know the gravity between myself and this marker. So I'm just going to change one of the two masses to be my mass, which is about 100 kilograms. That would be about 10,000 times the mass, and so the answer would get 10,000 times bigger, which would change this negative 13 to a negative 9. So much bigger, and you still can't notice it. You have a gravitational field, but you do not have the mass of a planetoid, so you will never notice it do anything. My own gravity, even this close to the marker, just no effect. Questions thus far? All right, let's mix it up one more time. Instead of two small objects, let's look at least one big object. Gravity between one 75 kilogram human and the Earth itself. Same formula, we're just going to swap out the masses and the radius. I'm going to input the mass of the planet first, and all of our best science indicates that Earth's mass is approximately 5.98 times 10 to the 24th kilograms. Single largest object you will ever likely encounter in your life. And then 175 kilogram human. Now there's an interesting thing here with the radius that we need to use, because this formula defines radius as the distance between the centers of mass of the two objects. If you're the human here, what is your distance between you and the surface of Earth? Sorry about that. What is the distance between you and Earth's surface right now? It's not a trick. 0. You're on Earth's surface right now. And so if the formula asked us to use the distance between the surfaces of the two objects, that distance would be 0. Here's Earth. Here's you standing on it. 0 distance. And so we put a 0 here, and then the formula stops working. That would say that there's somehow 0 gravity between you and the planet, because that's not how the formula works. The formula asks for the distance between the centers of mass, because the center of mass, the core of the object, is the center of its gravitational pull. For humans, that's usually somewhere in here, and for the Earth, it's the core. So the number we need is actually Earth's radius, because that's the distance you are standing from Earth's core, coincidentally. And Earth's radius is averaged over its weird, lumpy, technically oblong surface. The Earth is not perfectly round. It's kind of oblong. But the average is considered to be 6,378.1 kilometers. Meaning we need to turn that into meters first, which is 6,378,100 meters between us and Earth's core most of the time, and then that number gets squared. Again, being very careful with your calculator is very important when you are working with very extreme numbers. So make sure you keep track of where everything goes. And when I did this earlier, I got about 735 newtons. Does anyone disagree? Now, I find that number interesting, because we can use the old-fashioned method to also try to calculate this person's weight, right? If we did 75 kilograms times negative 9.8, just to check, just to see what this gives us, shock of all shocks, 735 newtons. That's because negative 9.8 comes from this formula. Basically, people did this formula, but removed the person's mass to calculate that acceleration. That acceleration, that negative 9.8, is big G times Earth's mass divided by Earth's radius squared. That is where it comes from. So this is kind of the broader, more general formula that was eventually boiled down into the more specialized version that we've been using. But just to prove that it works. Questions? All right. Well, we've now got just enough time to actually use this as a centripetal force in orbit. So we're going to do it one more time, but instead of Earth and person, it's going to be Earth and Moon. Moon orbits the Earth. We've already talked about the Earth's mass. The Moon's mass is 7.36 times 10 to the 22nd. It's actually only about 100 times less mass than the Earth. However, that 100 times is enough to weaken its gravity by 100 times outside of any other context like radius. So, might not feel like a big difference, but it is. And the Moon and Earth orbit each other at an average 384,000 kilometers apart. And if we have all that information, we can determine the force of gravity between the two. So pretty similar to the last one we did because it involves the mass of the Earth, but I'm just going to change mass to and radius. Instead of person mass, we now need moon mass, since that is now object 2. So another very big number. And then for radius, we need to take that very big number of kilometers, convert it into meters by multiplying by 1,000, and then square that. I'd say out of this entire semester, this formula, any questions that involve universal law of gravitation, are the questions that are going to have the most extreme numbers in them. So, all that said, what is the force of gravity between the Earth and the Moon? Sorry. Yep. Sorry, my ears aren't great. Yeah, 20th. 1.99 times 10 to the 20th newtons, which is an immense amount of force. If that amount of force acted on your body, you would immediately be transformed into Earth's flattest pancake. That somehow includes your bones. So it's a very large amount of force between these two objects. They are very far apart, but the masses of both of them multiplied together is enough to overcome that fact. Extreme amount of gravity. You need an extreme amount of gravity to cause something the size of the Moon to orbit. I will also try to use this as proof that there is gravity in space. Gravity does not turn off in space. There's gravity there. It gets weaker as you leave the planet, but it doesn't stop. The astronauts in the space station are not weightless. They're just falling perpetually. The astronauts are basically constantly going through those very expensive plane trips where the plane nosedives and you feel weightless inside the cabin. They're just going through that 24/7. They are not actually weightless. They're just constantly falling because they're orbiting. Gravity does not turn off as you leave the planet. In fact, the acceleration of gravity at orbit height is like 8 meters per second squared. It's only like 1/10 as strong as it is on Earth's surface. There's gravity in space. A lot, specifically, if you're the Earth and the Moon. And first of all, any questions finding this number? All right. Now, in the case of the Earth and the Moon, this force acts as a centripetal force. So in the case of something orbiting something else in space, this is basically your starting point. The force of gravity between the two space objects acts as the centripetal force between them. So if I ever ask you an orbit question like this, which there's an orbit question on your homework, and there will be an orbit question on both test 2 and the exam, this is the main crux of the problem. The force of gravity between the two objects acts as a centripetal force. Meaning you can use the force of gravity formula to find a number for centripetal force, and then set them equal to each other and proceed from there to find whatever you need to find. In this specific case, we are going to figure out the speed of the moon, how fast the moon is moving such that this orbit is possible. And to do that, we again have to set Fg equal to Fc. I'm going to write in the full formulas just to demonstrate. So here we've got universal law of gravitation. Fg is this. Centripetal force, meanwhile, is mass times centripetal acceleration. So I've just kind of gone in and substituted in the centripetal acceleration formula. I want to point out these R's are the same. Because since gravity is acting as the centripetal force, the radius, the distance between the centers of the two objects, the centers of their gravity, is the same distance that it will orbit at. So in this example, this distance that we used to find the strength of the gravity is the distance that the moon is orbiting the Earth at. So it's the same R on both sides. Same variable, same number even, which means you can actually do some canceling out shenanigans. I'll also point out that you often need to consider what mass goes on this side. And the rule is, and the centripetal force side of this interaction, that mass is always the mass of the orbiting object. This force of gravity causes the moon to orbit the Earth. The moon is the object that is accelerating centripetally, so the centripetal acceleration acts on the mass of the moon. So this M is the moon's mass, not the Earth's, or not even some third thing. It's moon mass again. This formula, centripetal force, it always acts on the orbiting object, the object that is physically moving in a circle. So in this case, if we want to use this to find the speed that the moon is orbiting at, we've already found a number for force of gravity. So I'll just write that in over here. Bless you.
Thank you.
On this side, we've got massive moon, which is the 7.8 times 10 to the 22nd again, times v squared over r, and it's the same r we used earlier because that is still the distance between the two objects. But you have to convert it to meters again. So still very big numbers, but this is how you would attempt to find the orbiting speed of an object in space. Force of gravity acts as a centripetal force, so you can set the two formulas equal to each other. And if you work it through right, please check your work and let me know if yours disagrees. You find that the moon is moving at about 1,000 meters per second. Every second, the moon rockets over 1,000 meters forwards. That's about Mach 3, 3 times the speed of sound. The moon is booking it. And that's just the speed it moves around us. It's moving even faster when you consider that we, therefore the moon, are orbiting the sun super fast. So this is just from our frame of reference. Moon's booking it. Questions? Okay. There is a second version of the centripetal force formula if you wanted to find angular speed instead of linear speed. You can use that too, just changes which version you're using, but it's still the same R, you're still solving for a velocity. That said, the moon's angular speed is actually very slow because it takes 24 hours to do 1 lap, approximately. So, angular speed is slow, linear speed is fast. How you guys feel? Questions, concerns, anything on your minds for right now? All right. Last detail I'll point out before we break for the weekend. This formula, the universal law of gravitation, the number you get out of it is the force that both objects exert on each other. Newton's third law tells us that if one acts on the second acts back on the first. So if the Earth pulls the moon towards it with this force, the moon also pulls the Earth towards itself with this force. So there is, as we speak, this much force from the moon trying to pull the Earth towards the moon. The reason that the Earth doesn't move because of this is because the Earth's just too big. Earth's mass is gigantic. The acceleration here would be like less than 0.0001 meters per second squared. So the Earth's not going anywhere because of the moon. The Earth's just too big. And this is one reason why, actually it's the reason why, Pluto's not a planet anymore. Pluto's mass is so small that the force from its own moon is enough to actually measurably make it move. Earth's mass is so big that this is nothing. Pluto's mass is so small that the force from its own moon is enough to make it start moving. So whereas the moon orbits Earth and the Earth doesn't budge, Pluto and its moon kind of do this. They orbit each other. And that's why it's not a planet. They changed the rules so that that disqualifies it from being a planet. Main thing you guys need to remember again is this formula acts both ways, A on B and also B on A. It's an inward force between both. Cool? This also means that if I say weigh about 1,000 newtons, I am exerting 1,000 newtons back on the Earth. But again, that's not enough to make the Earth move. But technically, Earth weighs 1,000 newtons on planet B. So that's one way to think about it. Need anything before we break for the weekend? All right. Ponder this information. Ideally, try to work on the Chapter 7 homework. Let me know if you have any issues with that. And next week, we'll continue talking about rotating things. Have a great weekend.